All right, ladies and gentlemen, welcome back. We're looking at empirical and molecular formulas today. Uh, Basically, what we're looking at here in terms of empirical, what it means is uh, the experimentally determined amount. So what that means is it's a common method for revealing the simplest, squeeze it in here, formula of a substance from a chemical analysis. So what that means is the most simplest ratio of elements. Okay? So it's the simplest, for example, C and O is a 1-to-1 ratio. That is the simplest. C2O2, that could be reduced to C1O1. So that is not an empirical formula. We'll show you what that is later. So how do you find the simplest ratio? Usually what's going to happen is they're going to give you the percent composition, like we saw last day. And what you use is that percent composition to find the mass, to find the mass of each element. And then once you have that mass, what you can do is you can use that mass to find the number of moles. So find the number of moles using that mass of each element. Because all the formula is, for example, CO, it's a relationship. So this would mean 1 mole of carbon for every 1 mole of oxygen. So if we know the moles, we know the formula. But if we do that conversion, sometimes you get some decimal numbers, and we don't have decimals as subscripts. So what you need to do is find the smallest relationship in terms of whole numbers between those elements. So find the smallest whole number ratio of moles. And for the most part, that's going to be where we stop. In order to find the smallest whole number, what we need to do is divide each value by the smallest number of moles. And we'll see some examples in a second. And like I said, usually that's as far as it goes, but if you don't get a whole number after this, what you can do is multiply each value by the same whole number, and that will give you your final subscript for the elements. So this will give you the subscript, which means just the number below the element. Okay, so there's a little rhyme that you can use to remember this. It's a little silly, but you know what? It works. So we say percent to mass, mass to mole, divide by small, multiply till whole. And that will cover all of our steps. So what we have here is I have 3 examples. We're going to do one together, so I want you to watch me do it. And then I'm going to give you a chance to pause it and try the next. And if you get that next one right, you don't have to worry about the third one. And if you don't get it right, you should probably go and try that third one as well. So let's look at this. The first thing we're going to do is it gives us the percent composition by mass of each element. So what we do is we take that mass, or that percent, and we change it straight into grams. And the reason why we're able to do that is because this adds up to 100%. And if we take these two numbers, they add up to 100% as well. So now what we're able to do, so that's step 1, just change it directly. There's no conversions, just straight up whatever the percent was will be the mass we're starting with. The whole goal of that is to get to mass, because if we have mass, we can change those into moles. So that was grams of magnesium, this was grams of nitrogen. The molar mass of magnesium is 24.3 in 1 mole, and the molar mass of carbon is 14.0 in 1 mole. When we multiply that out, we get 2.97119, and it would go on, but we just got a pretty good set of values there, and we can stop. 9857. So we multiplied it, we have our moles, but we're not happy with that because it's not realistic. We wouldn't put that down as our subscript. 2.97 isn't close enough to 3 to make it work. 1.98 isn't close enough to make it work. If it was 2.99995, sure, we could round, but you can only round if it's almost exact. So the next part was divide by the smallest one. Smallest value is this, and we do it to both. And then what we get is 1.4962, and we get 1, obviously. Still here, 1.496 isn't close enough to a whole number. It's very close to 1.5, and we know that if we have 1.5, if we multiply it by a certain number, we can get a whole number. So if we multiply this by 2, and this by 2, we're going to get 3, and we'll get 2 here. And now we have these nice whole numbers that we can use for the subscript. So the whole formula would be magnesium 3, nitrogen 2. And if you're wondering why I multiplied by 2, well, we know that 1.5, anything with a 0.5, if we times by 2, it'll create a whole number. The only numbers you're ever going to have to try out is pretty much 2 or 3, maybe sometimes 5. So hopefully that wasn't too complicated, but let's look at it again. So here's the second one. So what I want you to do, look back up at the steps that we did and try this yourself. Okay, so pause it now, and when you come back, it's going to be, the answer will be revealed and you can check it. We did the same thing. We changed it into the grams of each. We changed them into moles. We divided by the smallest one. But as you could see there, we didn't need to go any further because what we got was 4.0, 6.0, and 1. They're all whole numbers, and it's the lowest ratio between them. So we don't even have to do that last step. So here is our empirical formula. Simplest ratio between the elements. So if you didn't get that one right, try the next one as well. Okay, so if we're looking at this one now, as you can see, we did the exact same thing. We took our percentages, changed it into our masses. We converted from mass to moles, and then we took our simplest number, or our smallest number, and we divided all of those numbers by that term. What you can see is that, again, we didn't need that last step because we had these perfect numbers. And now we have our formula, which is ZnC1O3. Okay, so the next part we're going to deal with is the molecular formula. This by far gives people the most grief because it's a little bit more steps involved. So what the molecular formula is in comparison to the empirical, all it is just a multiple of that empirical formula. So for example, HO, if it's a molecular formula, there's all sorts of variations that you could have. You could have H2O2, you could have H3O3, but either way, all we did was multiply each by 2. CH, if we have CH2, C2H2, we multiply that by 2. If we wanted to multiply it by 3, we'd have C3H3. NO, we could just have it as NO. Sometimes the empirical and molecular are the same. All that means is that the ratio is 1. And the last one, we can make it up, and N2O4 times it by 2. Sometimes you can times it by 6. It doesn't matter as long as you know that the difference between the two is just some whole number multiple bigger. So let's look at the formula. Here's an example. A compound has an empirical formula of this, great, thank you, and a molecular weight of this, which means the molar mass. And you can tell it's molar mass because it's grams per mole. It wants to know the molecular formula. So we just said the molecular formula, all that means is that it's the empirical formula times some number. So we just call that number, we can call it X, but we'll just call it N for any number. And what that does is it allows us to define this. It already gives us this empirical formula. If it didn't, we could find it because we know how to find empirical formulas from the lesson that you just saw previous. So the big thing is we got to find N, and that's just how much bigger it is, how much bigger the molecular formula is than the empirical. So if I said how much bigger is a 400-pound person than a 200-pound person, you'd say, well, twice as big. So what we're trying to do is we want to find the molar mass and divide it by the empirical mass. And that will tell us how much bigger the molecular formula is than the empirical. So let's look at it. It gives us the empirical formula. So we can find the empirical mass. And it gives us the molar mass, so all we have to do is just divide. 98.96 grams per mole. In order to find the empirical formula mass, all we have to do is add it up. Chlorine weighs 35.5, carbon weighs 12.0, hydrogen weighs 1, but there's 2 of them, so 2.0. And when we add all that up, we end up getting 49.5 grams per mole. If we put that into our trusty calculator and divide it, you get 2. So what that just told us is that the molecular formula is twice as big as the empirical. Since the empirical formula is ClCH2, if we times that by 2, we end up getting Cl2, C2, and H4. And that is our molecular formula that's twice as big as our empirical. So what I want you to do is you can look back at this to see if you don't know how to do it, but try out this formula right now. Okay? Okay, so as you can see, I abbreviated a little bit here just to save some time, but the molecular formula doesn't change. It's just the empirical formula times some number. In order to find out what that number is, you just got to see how much bigger in terms of mass the molecular formula is than the empirical. So the molecular mass, it gives it to us, 104. Empirical, we added it up, carbon's 12, hydrogen's 1, so it's 13.0. So when we divide them, whoa, barely see that, it's 8. So that just means that the molecular formula is 8 times as big as the empirical. And so here's our answer. Unfortunately, it's not always that easy. In those two examples, it gave us the molecular mass, the molar mass, but it's not always going to do it. Most of the time it's not. So what we're going to have to do is find it ourselves. But luckily, we know anytime we want to find the molar mass, and this is kind of what we've been focusing on, it's grams per mole. That's the unit. So as long as we can find grams and moles and divide them, we can have the molar mass. So here's an example. If it gives us moles and grams, we know that the molar mass is grams over moles. So since it gives us grams, take it, write it down. It gives us moles, take it, write it down. Divide them, and we end up getting 71.0 grams per mole. So now that's the molar mass that we can use to find the molecular formula. A couple other scenarios that it might have for us is if it gives us density. We know that density is mass over volume, as it shows you right here. We know that molar mass is mass over moles, so grams per mole. So if we have mass over volume, it's an easy conversion because it's at STP. 1.43 grams over liters. We don't want liters, and luckily we have a conversion to get it out of liters and into moles. Cancel our units, and when we divide, we're going to end up getting 32.0 grams per mole. Once again, that's our molar mass that we can use to find our molecular formula. And the last situation is that if it just gives us mass and volume by itself. But we know that mass and volume is density, and so we can just create a scenario like that. We know that the molar mass is grams per mole. That's what our goal is. It gives us 0.135 grams, so we're almost there. But instead of moles, it gives us liters. But with our knowledge, we know that since it's at STP, we can take that 22.4 liters and put it over 1 mole, cancel off the units, and it leaves us with grams per mole. We can go 0.135 divided by 0.0425, get your answer, times it by 20.